Welcome back to Physics 141 Online. Today I'll start with a review of some of the common forces that we encounter in mechanics problems. Then we'll move on to the techniques for drawing accurate free body diagrams. And finally, we'll close with doing some example problems where Newton's second law is used to calculate information about the motion of objects. So just to remind you again, weight is the force that a massive object like the Earth exerts on other objects near its surface. And the weight for a mass m always has magnitude mg and is directed downward toward the center of the Earth. We also have forces where objects are in contact that share a surface of contact with each other, and because the force is perpendicular to that surface of contact, like we see with the box on the table, we call this the normal force. And in this problem there's a force of the table acting upward on the box, and there's also the force of the box acting downward on the table. And Newton's third law tells us that these two forces are equal, although they're opposite in direction. Then, sometimes we have problems involving springs, and the force that the spring exerts on the object it's attached to is given by Hooke's law. The minus sign in here indicates that the direction of the force is opposite to the displacement of the object, so that if the spring is compressed, the force is against the displacement. If the spring is stretched, the force again is against the displacement. And K here indicates that this equation is a linear equation between the displacement and the force. And finally, we have string forces, or forces that are exerted by a string on an object that it's connected to. And this string force can be upward or downward, just depending on the nature of the situation, or sideways, depending on the diagram. And we usually use the symbol T to indicate a tension force. And if we have a string that is wrapped over a pulley, for example, like this, if we can make the assumption that the pulley is massless and moves without friction, then we can assume with a pretty good degree of approximation that the two tensions in the two ropes are the same. And so we will often make that assumption. All right. Now we move on to what we actually have to do, the steps we have to go through to use Newton's laws to solve problems. Remember, mechanics is all about calculating information about the motion of an object from information about the forces that act upon that object. And how do we determine the forces? Well, we first have to draw what's called a free body diagram. Make sure, and this is really important, that on your free body diagrams you only indicate arrows for the forces that are acting on the object. And remember that velocity and acceleration, which may well describe the behavior of the object, those are not forces themselves. Acceleration results from a force, but acceleration itself is not a force. So here is an example that we will see often in problems. There are lots of cases where we have an object resting on an inclined plane and sliding down that surface when we release it. The arrow indicates the direction of motion, and the incline makes an angle of theta with the horizontal. So if we want now to draw a free body diagram for this mass m, we represent that mass by a point in a separate diagram. It's always important to draw the free body diagram separately from the original sketch showing the physical situation. So the dot represents the block of mass m. I like to draw in a dotted line when there's a surface like the inclined plane here involved to indicate directions. So perpendicular to the surface of contact is the normal force, and it's the force of the plane acting on the block, and so it's upward and to the right as indicated by the arrow n. Then there's always the weight, because presumably this problem is occurring at or near the surface of the Earth, so there's a weight force mg downward, and those are the only two forces that are acting on this object, assuming that the plane is frictionless. So there's one more thing though that we have to do, and one of the steps in problem solving using Newton's laws is to choose a coordinate system, and we will find it convenient in a problem like this to choose a coordinate system where one of the axes is directed parallel to the ramp, because that's the direction that the object's going to move. And what that means then is that the weight vector mg has components along the ramp and also perpendicular to the ramp. So often we will then sketch in a right triangle where the force vector is the hypotenuse, and the two sides of the right triangle are respectively the x component and the y component. And in order to determine what those are, we have to put the angle theta into that triangle, and a little bit of comparison will convince you that the angle theta in the sketch of the plane is the upper angle in that right triangle as shown here in the sketch. And so that would be a complete free body diagram for this situation. The idea problem-solving strategy, the steps that we want to follow, include the following. Draw a neat diagram that includes important features. That's before you do the free body diagram, just a picture of the physical system involved. Then we draw separate free body diagrams for each object of interest, and for each object choose a convenient coordinate system. They don't have to be the same for each object, but as soon as we define a coordinate system, we have to be consistent with that all throughout the problem. Thirdly, we write down Newton's second law in component form, which means that we add up all the x components of the forces and set those equal to the mass times the x component of the acceleration, and so on. Fourthly, if we have more than one object, where we have two objects that exert forces on one another, then we'll use Newton's third law and any kind of constraints to simplify the equations from number 3. These constraint equations are important because often we have two objects that move and their accelerations are related to one another. Sometimes they may be equal, sometimes they may differ by a minus sign, and that's important for us to take into account. Finally, number 5, once we've written down the equations that we can think of, we need to count the number of equations and unknowns. And you know from your study of mathematics that if you've got 3 unknowns, you need at least 3 equations in order to be able to solve for those. So then we go ahead, solve the resulting equations for the unknown. And finally, once we've got a solution, we check our answer for units, physical plausibility in the case of a numerical answer, and there might be familiar limiting cases. For example, if there's an angle theta involved for an inclined plane, we may be able to check our answer for the limiting cases of theta equals 0 and theta equals 90 and see if the answers make sense in those familiar limiting cases. So those are the steps that we'll follow consistently in all problems involving Newton's laws. So here's the example. I'll explain it and then I'll go to my tablet so I can solve it for you. These two blocks rest on a horizontal surface that has negligible friction. We're going to assume no friction here. They are connected by a string that has tension T, and then we apply a force horizontally to the first mass, m1, and cause the blocks, because of that force, to accelerate to the right along the surface. The unknowns, the things we're trying to solve for, are the acceleration of the two blocks and the tension in the string in terms of the masses and the force F. So since m1, m2, and F are given, those quantities symbolically can appear in the final answer. Okay, so here's that problem in a format that I can apply on my little sketch pad, and I've resketched the physical situation where there's a force F that's applied to mass m1, which is connected to mass m2 through this string, and I'll put a T in for the tension in the string. That's one of the things we're trying to solve for. And we're also trying to solve for the acceleration of the system as the masses accelerate to the right. So, how do we start? We start with free body diagrams for the two objects. So I'll just draw them as they are in the sketch. We've got m2 on the left. So clearly there will be a force due to the tension in the string that will be pulling m2 to the right, so that's T. Also there's a force of the surface pushing upward, and that's what we call a normal force. I'll call that N2 to distinguish it from N1 because there will be a normal force on mass M1. And finally there's the weight, which is the Earth pulling down on mass M2, and we know that that's W2, we can call it, but that has magnitude of M2G, and I might as well put that into the sketch at the very beginning. Then for M1 there will be, I'll label it as M1 in just a minute, there's the force F pulling to the right. Notice that the force F is applied to M1, not to M2. And so F, of course, is the force that causes both masses to accelerate, but F is only applied to M1, and so it only appears on the diagram for M1. There is likewise a weight that we could call W1 or M1G. Then there is the normal force, the force of the surface, the table, for example, pushing upward on mass 1, so that's N1. And also now, the string is connected to M1, so it exerts a force on M1, and that pulls to the left. All right, the string doesn't push M1, it actually pulls it backward to the left. We see here that this tension, I will use the same symbol because there is only one string, and the tension must be the same throughout the string. So, these are the two free body diagrams. Now we need a coordinate system, and this is a fairly simple choice in this case. The standard horizontal x and vertical y coordinate system makes sense here. The reason we choose it is because the motion of the system will be to the right, and in a problem like this, almost always we choose a coordinate system where the direction of the acceleration is along one of the coordinate axes, and here it will be along the x direction. So now we're ready to use Newton's second law for these two masses. Realize again what we want to solve for. We're trying to solve for t, and we're trying to solve for the acceleration. There's no friction in the problem, and so we will not need to consider that. And the motion being horizontal means that we really don't have to worry about the forces in the vertical direction. We could solve for the normal forces N1 and N2, but we're not asked to do that. So I will start with just the horizontal forces. So here's the way we do it. We apply Newton's second law along each direction. So here we take the sum of the forces along the x direction, and we set that equal to the mass times the acceleration. So I'm going to do it for M2 first, and I will call this A2x because A2 has an acceleration. It's along the x direction, so this is the x component of its acceleration. And I will indicate that this is for mass M2. It's pretty clear from the right-hand side, but let me just put a little M2 with a circle around it. So we'll add up all the forces in the x direction and set them equal to M2 A2x. Then for M1, we'll do the same thing. We will add up all the forces along the x direction for it and set that equal to M1 A1x. And there is a relationship between these two accelerations. We'll get there in just a minute. First of all, for M2, along the x direction, we look at the free body diagram. There's only one force, T, and it's in the positive direction. So we have T equals M2 A2x. Now, I can't stop here because we're trying to solve for both the acceleration and the tension. So this is one equation with two unknowns in it. So I'm not ready to solve for either one of those yet. For the second equation, for mass M1, we see that there is a positive force, F, and there's a negative force, T, just looking at the free body diagram. F is in the positive direction, T is in the negative direction. So F minus T equals M1 A1x. So we look at the two equations now, and there are actually three unknowns because T is unknown, A2x is unknown, and A1x is unknown. So we've got two equations with three unknowns. That's a problem. But now we add to the list an equation for the relationship between the two accelerations. And I always call this the constraint equation because since the two masses are connected, as long as the string connecting them does not stretch, then when they move, they have to move rigidly together so that the acceleration of mass 2 along the x direction will equal the acceleration of mass 1 along the x direction. And that may seem really obvious, but in some problems the relationship is not this simple. So I always like to make it an extra step so that we reason it out and think about how the accelerations are related to each other. But now we've got three equations with three unknowns. So I'm going to call call this one here, because it's for mass m2, I'm going to call it equation 2. This equation I will call equation 1 because it's for mass m1, and we'll call the constraint equation equation 3. So now we're going to solve. We've actually worked through the idea or identify step up here when we were drawing the sketch and thinking about how to use Newton's laws. Then we are in the D stage here, where we drew the free body diagrams and developed the techniques for the solution, writing down Newton's second law for each object. And now we're going to evaluate and solve for the unknowns in this problem, which again are the acceleration and the tension. So to solve for the acceleration, let's see what we can do. I've got the unknown. One of the unknowns is tension, and so I probably would like to get rid of tension in these two equations. So I'm going to plug equation 2 into equation 1. Because equation 2 solves for t, I'll take that and plug it into equation 1 and thereby rewrite equation 1. So I've got f minus t, but t is m2 a2x, and now that equals m1 a1x. All right, now the second step is going to be to now sub in equation 3, because equation 3 tells me that a2x is equal to a1x, so I'll just rewrite this and replace a2x with a1x. It becomes f minus m2 a1x equals m1 a1x. Now I want to solve for a1x. That's my only remaining unknown. So to do that, since the term appears twice, I need to get the a1x terms on the same side of the equation. So I'm actually going to add m2 a1x to both sides. So that gives me f equals m2 a1x plus m1 a1x. Now I'm going to factor out the a1x term, a1x, right, from this equation here. That gives me f equals a1x times m2 plus m1. And now I can solve for a1x by dividing both sides by the sum of the masses, and I get a1x equals f over m2 plus m1. This is one of my desired results, because we were supposed to solve for the acceleration. Now we've got the acceleration, let's go back to solve for the tension. And the easiest way to do this is solve for t from equation 2. And the reason I can do that is it says t is equal to m2 a2x. Well, a2x is the same as a1x, and I have a1x here, right? So it's m2 times the quantity f over m2 plus m1. There's not much more I can do to simplify that equation, and so we're pretty much done with the solutions for acceleration and tension. All that's left for us to do is assess the answers. There's not too much we can do because I haven't given any numbers numerically. We can't ask whether the answer makes sense numerically, but we can check units again. So units, if I look at the equation for A, well, that one's pretty simple, right? Because F should be equal to a mass times an acceleration. And we can check that from Newton's second law directly, and clearly that works. That's right. Let's look at equation 2. It says the units of tension should be, right, the units of, in this case, m2 times the units of F over the units of the sum of the masses. And this is nice because I've got a mass term on top and on bottom, right? So the units, whatever units I use for those guys, cancel out, and the units check out because now what I'm left with is a tension, which is a force, and the units for tension should be equal to the units of the force that's applied horizontally, and they work out okay. So the last test indicates that both these results make sense from the standpoint of units, and indeed they are correct. So this problem is a really good prototype for lots of problems that you will solve in the homework. This one's very simple because the only forces we need to worry about are along the horizontal direction. Realize, of course, that there's more information here. If the problem had asked us to find the normal force on block 1 and block 2, we easily could have done that by adding up the forces in the y direction and setting them equal to mass times acceleration in the y direction. But we didn't have to do it. So for this problem, we're finished. And you'll get practice doing problems like this on the homework assignments.